All right, what's going on, you guys? Another LeetCode video today. This one is called Binary Tree Maximum Path Sum. So they basically give us a binary tree and they want us to return the maximum path sum. So what that means is, let's go over some definitions that they give us. So a path in a binary tree is just going to be a sequence of connected nodes. Where they're connected, it's just nodes, a sequence of nodes connected by edges. A node can only appear in the sequence once, right? There's not going to be cycles. This is a binary tree, so I'm not sure why this is mentioned, but obviously there's not going to be any repeated nodes, right? So the path does not have to pass through the root, so the path can span anywhere in the binary tree, and basically the path sum by definition is just the sum of the node's values in a given path. So, and they want us to return the maximum path sum of the whole binary tree they give us. So there can be negative numbers. So potentially, like when we're at a node, it could actually just be taking away from the max sum we're looking for. So that's something important to consider. So the way I'm going to approach this is I'm just going to use a recursive depth first search. As can be applied to many tree problems, but for this one, recursive depth first search. So let's start talking about that algorithm. There's one global variable we need, which is just that max path. Or the max path sum, really. Right, so at first, this is just going to be negative infinity, right? It's not going to be zero because there are negative numbers, right? So imagine if we had a tree that was just filled with negative node values. Well, the maximum path sum, would have to be a negative value. So this is going to be negative infinity at first. All right, and so for our recursion, we're going to have to seed that at the root node. And basically, at every single node, we're going to consider two things, right? So the first thing we're going to consider is just what the maximum path is at this node. So if we were to consider both the left and right children as belonging to the path, well, we cannot extend upwards anymore, right? Because a path can only go one direction from this node. So there's two things we have to consider. The first thing is, what is the maximum path that includes this node? So and includes both of its children, right? So we would have a path that goes something like that, or maybe something like this, but it cannot go like this and like that, right? So that's like the main idea I want to convey there. So we have to consider basically paths that are under this node, right? We can't go up. Okay, but the next thing what we need to do when we pop back up from this node, though, is we can only consider one direction, right? Because again, if the path goes this way, it cannot go to both children. We basically, when we're popping back up from our recursion, we can only choose the maximum gain, basically, from either the left or the right child. So now that's out of the way, let's just start iterating through the recursion and kind of acting like we were executing this function. So first, obviously, we seed with this number. The first line of code we're going to have is going to check for a null pointer. And when there's a null pointer, we're going to add 0 basically we're going to return 0 as the max gain from that path. And then after that, we're going to call recursion on the left child, and then the right child. So we're not at a null node, and there's a left child, so we're going to go left. We're going to keep going left, and we see that there's a null pointer here, so we'd return 0 as the max gain from this node. So I'm just going to write that. So every time we return something, I'll specify. So this is going to be 0. And then we're going to pop back up, and we can search right now this way. So let's search right, and we're going to return 0. And then we're going to pop back up. Okay, and now once we've basically explored both subtrees fully of a node, we can now consider, okay, is this node, is the maximum path sum so far going to exist, below this node? We need to check that. And how do we calculate that? Well, we would basically just add the max gain from both children and then just the value of this node. So this node's current maximum path is going to be 9. But that's not the value we're returning. But we want to compare that to the current max path sum, which is negative infinity, and then see which is greater. So the current path sum at this 9 is going to be 9, right? And that's greater than negative infinity. So we're going to have a new max path sum that is 9. Okay, so now we need to return something at this node, right? And we don't want to return some of these. We can only choose which path or which child gives us the most gain, right? And they're both 0, so it doesn't matter. So we can just return, it's going to be 9 plus whatever the max is there, and it's both 0, so we just return 9. Okay, so now we're going to pop back up, and we're at this 10. Well, we need to keep searching, right? Because there's a recursive call on the right child. Okay, but we always search left first, so we're going to keep going left. And then down here, again, we'd return a 0 because it's null pointer. And then we're going to pop back up, but we don't want to do anything yet. We need to keep searching because the right child hasn't been searched. We see that there's a 0 here. So let's pop back up, returning 0. Okay, and at this 15, now we need to check, is this current path, below this 15, going to be greater than our max path sum? And it is, right? Because 0 plus 15 plus 0 is greater than 9, right? So our new max path sum is going to be 15. Okay, and now at this point, we want to just return whatever the greatest, basically the most gain we can get from either the left or right child, the left or right subtree. So, and that's going to be, it's both 0, so 0 plus 15 is just going to be 15 here. Okay, and then we're going to pop back up to the 20, and then we have to search that right child first, and then we go left. So that's going to return 0 as we did before. Pop back up. Now we need to search right. We're going to return 0 and then pop back up. Okay, same thing here. Is the current max path going to be bigger than our our overall max path sum? No, because 7 plus 0 is not greater than 15. So we're just going to move on. Well, we need to return something first, right? So this is going to return 7 because 0 plus 7 plus 0. Well, no, that's what we just compared. Actually, what we'd return is just one of these zeros, right? Sorry, the greater of the two. So, and they're the same, so just 7 plus 0. Okay, and then pop back up to this 20. Now we want to see if this current path in here gives us the max path sum that's greater, right? So basically a path that's like below this, including this 20, but below the 20 and below, right? So to do that, we would add the max left, which is 15, with the max right, which is 7, and then also with the value at this node currently, so that would be 42. And then we would compare, sorry, it's not what we're returning, we're just comparing 42 with max path sum. That's clearly greater than 15, right? So we have a new max path sum of 42. Okay, and then we would just, the value we'd return would just be the greater of the two gains, left or right, so the greater is 15 plus 20. We're just going to return a 35 here to be considered at high nodes that are higher up the tree. Okay, so then we move back up. We're going to consider nodes including this 10 and then both left and right subtrees. So we would take minus 10 plus 9, that would be minus 1 plus 35. So 34, that's not greater than 42. And then the value we're going to return is just minus 10 plus 35, so 25. And obviously this is irrelevant because we've already found the max path, but the algorithm would technically continue to execute to ensure that the max path doesn't occur higher up the tree. So we'd pop back out of a recursion like that, and then our answer would be this 42. In terms of the time and space complexity for this problem, it's pretty straightforward. The time complexity is just going to be big O of n, where n is the number of nodes in our tree, because we're basically just doing a depth first search on every single node in the tree. So big O of n, time complexity, and then the space is going to be big O of h for the recursive call stack. We can have as many recursive calls as a time as there are levels to our tree. So it's big O of h, where h is the height of the tree for the space complexity. So let's go ahead and get into the code here. So the first thing that we'll do is we're going to need a global variable for that max path sum. And that's going to be negative infinity at first. So in C++, we can simulate that with the minimum integer. Since we're just working with integers here, and helpful to look at the constraints, but we can see the node values only go to negative 1,000, so we don't have to use like a long or anything like that. So we also want to seed our recursive function. I'll call it get max gain, and we're going to pass in the root, and then we're going to pass in the max path sum. There's just going to be 2 parameters. And then we'll return the max path sum. All right, so let's go ahead and write this function signature, and then also the declaration and definition. Let's knock both of those out because we need both of those for this to work. So we're gonna have an integer return value because we need to return whatever the greatest gain is in the path when we're popping back up in the recursion. So we need a tree node here. I'll call it Tn, and then we also need this max path sum integer variable by reference because it's kind of like a global. So the first thing we want to do here is just check if our tree node is null pointer, right? Because if it is, then we just want to return 0 there for that max gain. The next thing we want to do is do our recursion, right? So we're going to have store these in integer variables, the max gain in both children from both possible directions. So we'll say max left for the maximum gain we can get going left. That's going to be the max between we're going to call that function recursively on the left child, and we have to pass in the max path sum. And then it's going to be the max between that and 0, right? Because we can have negative values, and we don't want to be adding any negative values to our gain, right? Because this is by definition a gain. We're not concerned with decreasing our maximum path sum. We only want to increase it. So we're going to take the max of that and 0 to eliminate the chance of propagating up a negative value. So that's the reason for getting the max between that and 0 and not just taking the max gain directly. So hopefully that makes sense. So let's get the max right, and then it's basically the same code mirrored. Okay, and then we need to take the maximum path, including that node, and then both children, and then compare that with the max path, right? Because we want to consider including this node as the root node in the path. So the calculation we're going to do is we're going to say current max path sum. That's going to be equal to the value at the tree node plus the max we found left and the max we found right. Okay, and then we can just compare that with the current max path sum to update that. So we'll say max path sum. This is like the global value for that we're keeping track of for that. It's going to be the max of whatever that was previously, and then this current max path sum that we're calculating. Okay, and then after that, we want to basically just return the greatest gain from either the left or the right subtree plus the value that the node is giving currently. So the value of the current node. So whatever the values of the current node plus just the max between the max left and max right paths. So that's pretty much it for the problem. So let's go ahead and submit this and take a look at the percentages. So it beats 97% and runtime, and then 60% memory. So it's a pretty efficient solution. Hopefully this video helped you understand the problem better. If it did, leave a like, subscribe, all that stuff helps the channel. I really appreciate you guys checking the videos out, and I'll see you guys in the next piece.